Welcome to class, everybody. So, as you know, Halloween's coming up, and sometimes I hear from time to time students don't think chemistry is useful. I don't know if you've ever felt that way, that the stuff you're learning isn't useful. Well, we're going to find a useful way to use a chemical reaction to help us finish the carving of a pumpkin. So Angela Miller, our demonstration leader, is going to show us how to finish off the carving of a pumpkin with chemistry. You want to take it away?
I just heard the term demo diva. Thank you very much.
Demo diva.
So in this Whiteboard, I've got calcium carbide, which is CaC2. When you add it to water, it makes a settling gas, which is, flammable. So it's going to build up in the pumpkin, and then I'm going to light it on fire. So fingers crossed, because it is a big pumpkin. Takes about 20 to 30 seconds for enough of it to build up in there. It is loud, but not so loud you need to plug your ears or anything. I am wearing earplugs because I'm so close to it. But yeah, hopefully we can use chemistry to help us finish carving this pumpkin. Has it been like 20 seconds? Yeah.
The longer the better.
All right, we're going to try it.
All right, round of applause, guys. All right, that was pretty cool. All right, so chemistry's useful. All right. So the once when you go last, when you're like the last class to have the pumpkin explosion, you actually put one of those H2O2 balloons inside the pumpkin and blow that up, and the whole pumpkin just, I don't know, it almost like blows pumpkin everywhere. It's pretty cool. But anyways, okay, so I hope you guys have a happy Halloween. That's our little Halloween demonstration we tend to do every year. So let's get back into the material. I don't know how we go back to lecturing after that, but we'll try. So one of the topics in Chapter 8 we haven't talked too much about, we've kind of mentioned it but haven't gone through any examples or discussed the implications of this, is resonance. Resonance comes up with molecules like ozone. Let's try to come up, we see the Lewis structures here, but I want to make sure that we could come up with those same Lewis structures. So if we're picturing O3, we have a total of 18 valence electrons. So 3 oxygen, 6 valence electrons for each oxygen. So when we're coming up with our Lewis structures, we're kind of picturing the central oxygen. So one of the oxygens is in the center. The other two have to be bonded to that central oxygen. Whenever we have 3 atoms, they're just all going to be connected. Whenever the atoms are exactly the same, of course, it just goes O. We start with single bonds, apply maybe our general Lewis structure rules, and come up with this particular Lewis structure here. The reason why we might do this first is that uses 16 of the electrons. So I see that there's 2 electrons left to go, so that I know I need to put 2 electrons on the central atom. And so then once we get the right count of electrons on the central atom, we can then maybe notice the central atom only has 6 electrons surrounding it, so we look around the whole atom. That's only 6 electrons. That looks like a weird smiley face, but unintentional. And so then what we might do is notice that the oxygen has a 2+ charge. So the formal charge of oxygen right now should have 6 electrons surrounding it for a 0 charge, and it only has 4 electrons closest to it. So it only has those 4 electrons closest to it. This is like unintentional. I don't think I could redraw that if I tried. All right. I don't think this is going to help the face. It's going to kind of ruin it. But so then we're going to make the double bond. No, that's not bad. So we end up making the double bond, losing the electron pair here. And so then we end up with one of these Lewis structures here, where we have an oxygen with a minus charge. And then the central oxygen now has a formal charge of plus. And so then the big issue here with ozone is how you could notice that it has a second Lewis structure that is essentially exactly the same in what it's representing, yet it's still different. So we could have made the double bond with the other oxygen atom. So if we kick the other electron pair in, we could have made the other double bond instead and left the other one single. So it's a tricky concept to maybe notice that those two structures on the left and the right side here are different from each other, yet they're equivalent in what they represent. So whenever we have this case of what we might say different yet equivalent Lewis structures, we have this idea of resonance kick in, and it almost sends us back to an idea of Lewis structures that I've said a few times, is that the representations are not real things. So like a Lewis structure isn't really a real thing. Just because we can sketch resonance structure, let's call this one A and call this one B, just because I can sketch A and B doesn't compel the molecule to exist as A or B. Because it turns out the real molecule is always going to exist as the blend or the average of these two structures. So the real ozone molecule will actually always look more like this, where we have that extra bond averaging itself out across both of the oxygen-oxygen bonds. So we have like an averaging take place, if you will, at all times, so that we never have a double versus single, and it's not like an equilibrium going back and forth. It's really a case where the static molecule always has two equivalent bonds. So two equivalent bonds have exactly the same bond length. So we mentioned the connection of bond order to length a little bit, how triple bonds shorter, double longer, single longer. If you look at ozone, you would expect it to have two oxygen-oxygen bonds that are equal in bond length. So these two bonds are equal in length. And then you might describe them, you might say, well, how can you describe how long the bonds are? Because they're going to end up being a little bit longer than you expect for a double, but then a little bit shorter than you expect for a single. We could describe the, if you will, the bond order. And let's picture bond order for a second. Like for O2, this bond is a double bond. That's an order of 2. So the bond order for a double bond, you would say like the BO or the bond order is equal to 2. For a triple bond, you'd say the bond order, like between two nitrogen atoms, you'd say that's a triple bond. The bond order here would be equal to 3. So 3 for triple. So a bond order is just another way of expressing sort of the order of the degree of the bond. So single bonds, order of 1, double bonds, order of 2, triple orders of 3. And so what we might look at for ozone is for the ozone molecule, it's like taking 1, 2, 3 pairs of electrons and spreading them across 2 actual OO bonds. So what we're doing with these two molecules is we're taking 3 bonding electron pairs and spreading them across the 2 oxygen-oxygen bonds. So the bond order is like right between a single and a double that we'd expect for those OO bonds. So the order would be about 1.5. We just call it a 3/2 bond order. So the key is that both the oxygen bonds are exactly the same length, exactly the same order, and we only pick this up by noticing we could sketch 2 Lewis structures that are equivalent. When that's the case, we call them resonance structures, and the idea is that that electron pair is resonating at all times across those 2 bonds. So the electron pair just spreads itself out at all times across the bonds. Now there's some models for this within chapter 9 that show how this happens with orbitals. So let me show this with nitrate ion. So we've sketched nitrate before. We've come up with a structure, a Lewis structure that looks kind of like this one here. The issue with nitrate, we have this positive formal charge still on nitrogen. We have a 0 formal charge on the double bonded oxygen. And we have minus formal charges on the other 2 O's. We have the issue with nitrogen in the second row of the periodic table cannot expand its octet. It can't take in a second bond, a second double bond, so it has to stay with this plus formal charge here. And so now the issue for nitrate is you would imagine, we sometimes use this word localized. A localized bond is like a double bond that actually exists as a double bond in the real molecule. In nitrate, we're not going to have that localized bond. This is what it would look like in the molecule if you had a localized bond. We're going to pick up in chapter 9 that you'd have these 2 other orbitals of oxygen pointing in that same direction as the double bond orbitals that are making up that second bond of the double bond, and then you end up getting this simultaneous overlap of that electron pair. That simultaneous overlap is what's really describing the orbital picture for spreading out that electron pair across the other two oxygens all at the same time. And so for the case of nitrate ion, instead of thinking of the molecule or the ion as having two NO single bonds and one NO double bond, think of it as having three NO bonds that are of an order of about 4/3. So the bond order that we expect for the real molecule should look more like the 1, 2, 3, 4 bonding pairs of electrons that we see in the Lewis structure being spread across the 3 NO bonds. So we have 4 bonding pairs of electrons spread across the 3 NO bonds. So we'd expect maybe the bond length would be a little bit longer than we expect for a typical NO single bond. Or excuse me, the bond length we expect here would be a little shorter than we expect for the NO single, but then a little bit longer than we expect for the NO double. So if you think of like relative bond orders, I think there's a question towards the end of the notes that we'll get at sort of ranking bond lengths as an issue of their bond order. So as the order goes up, more bonding electrons is going to shrink the bonds, fewer bonding electrons will lengthen the bond. Okay, so now what we describe nitrate as having are these delocalized pi bonds. So a delocalized pi bond is how the molecule is actually spreading the electrons out across all the atoms at the same time. So what you can see is a molecule never exists with that localized bond. It only ever exists with that sort of delocalized pi bond. So it's like you have, if you will, 3 single bonds and then one of these extra pi delocalized bonds spreading those electrons out across the ion at all times. Now there's just a couple other pictures in situations where this comes up, and these pictures are still from chapter 9, but this just kind of shows us what this looks like and why we see this effect. Benzene is a molecule that looks like a 6-membered ring. So we might think of drawing the double bonds here. And so we'd have hydrogens at each of the corners. And then you could also probably notice and say, well, if we just have 3 double bonds, why don't we just shift them over to here and come up with an equivalent Lewis structure where the double bonds are simply drawn in a slightly different orientation. So if we draw the double bonds here, notice how that's a different Lewis structure. It's different in which of the carbon-carbon bonds are making the double bond. So between the two structures, it's like in one case, 2 of the carbon atoms either have a double or they have a single bond. If the molecule is really going to go back and forth, you might expect that sometimes it's going to be double, sometimes it's going to be single, and it's going to be going back and forth. But the real molecule doesn't go back and forth. It spreads those extra electrons out at all times across all of those carbon-carbon bonds. So if we're looking at the carbon-carbon bonds, I should also point out that this is kind of like an OChem thing of whenever you see a vertex without an atom noted that it's assumed to be carbon, that's more of a OChem notation. And so at every vertex is a carbon atom. And so if we look at the bond orders of the carbon atoms in this sort of ring here, you might look and say, well, what are the bond orders here? It's like either single or double, and there's 6 of those bonds across the molecule. We end up having a total of 9 of those carbon-carbon electron pairs. We have 9 bonding pairs of electrons spread across the 6 carbon-carbon bonds. So if I count like the electron pairs, if I count the lines in between the carbon atoms, it goes like single, then double, so that's 6, then so we get 1, 2, 3, 4, 5, 6, 7, 8, 9. So we get 9 bonding pairs of electrons spread across the 6 carbon-carbon bonds. Probably not so crazy when you see it's either single or double, so on average it's about a 1.5 bond, so back to a 3/2 bond order. So bond order we could say is like 3/2 in the case of the benzene molecule. Then we get this issue of resonance, where this is going to cause all those carbon-carbon bonds to be exactly equal in length and more of this order of about 3/2. So for picturing bond order here, we'd have our carbon triple bond shorter than our carbon-carbon double, then shorter than our benzene carbon-carbon lengths, and then less than the carbon-carbon single bond, with that 3/2 bond order right in between the double and the single in terms of length. So this is just kind of summarizing that the delocalized pi bonding is what leads to this spreading out. So hopefully by seeing a picture of what these orbitals look like, you can come up with an understanding that all those orbitals point in the same direction and the electrons are spreading out across the entire molecule at the same time. So we never have the case of delocalized bonding in these molecules. We never have the case of localized bonding, of having double bonds versus single bonds. We only ever have the case of having these 3/2 type bonds or 4/3 type bonds in the nitrate ion. Never the case of localized bonding when we have the case of resonance. Okay, so let's just address that question of localized bonds and think of a couple molecules where we have to figure out if we have this case of resonance taking place or not. So this question here is looking at a couple Lewis structures, so we have to be able to go through and sketch those Lewis structures. So the first molecule that we're looking at here is formaldehyde. Then OS2 is a somewhat strange molecule of oxygen where it bonds with fluorine, and then the carbonate ion. Then we're also looking at the word localized. So a localized bond is like a real double bond. So we're trying to choose which molecule has an actual double bond that exists between two atoms that doesn't spread itself out across the whole molecule. Okay, give this question a try. Bless you. It's probably the vaporized pumpkin. Well,
I just don't know. Like I had oxygen, so I just don't know how you.
I suppose it's through like a little bit of trial and error, or it's like how else could you get 4 bonds to carbon? I'll talk about that a little bit on how. Okay, so well, actually, we have this question. All right, one more minute, then we'll go over this one. Okay, so good. Let's take a look at this one. I had a question on how we knew to come up with this Lewis structure for the first one. So in terms of like the Lewis structures here, arriving at the right Lewis structure, for like CH2O, I think what I'm thinking is the hydrogens are going to be connected to like whatever atom comes before it. So the 2 hydrogens definitely on the carbon, and then the oxygen would have to go onto the carbon at that point. So the hydrogens aren't going to bridge 2 atoms together. So hydrogens are always going to be on the outside, never bridging between atoms. And then sometimes there's a bit of trial and error that if you were to try to put oxygen in the center, that the question would be, how do we arrive at 2 bonds, 2 lone pairs for oxygen in the center here? It's going to be kind of hard to come up with this. So sometimes it might be a bit of trial and error with some of the Lewis structures, in particular maybe with some of the organic compounds. But so we arrive at this Lewis structure. You may have had the Lewis structure where you had the single bond with the extra pair of electrons on oxygen first, but in that structure you'd be looking at the formal charge of carbon pulling in that extra double bond. You may also be looking at this where carbon should form 4 total bonds, and we get 4 bonds with the double bond to the oxygen, single bonds to the hydrogen. Now, of course, this is the case where this double bond is right there between those 2 atoms. It's not going to spread itself out to the hydrogens. So that is the exact case of the localized double bond. OF2, maybe an interesting example to talk more about its Lewis structure, just to pick up how we take the central O, connect the 2 Fs, give the Fs their octets, and then pick up the 4 electrons that are left over to go on oxygen. It's interesting to see that this molecule exists with 0 formal charges in its Lewis structure, probably why it exists as a, not necessarily the most stable molecule, but it exists as an actual molecule you can synthesize. And this is also one we noted back as early as chapter 4. Remember the oxidation numbers? We would assign the oxidation numbers of minus, minus, and plus 2. It's a good reminder for these are the oxidation numbers, but the formal charges would all be 0. So formal charge and oxidation number are 2 different things in what they're representing. The oxidation numbers are getting more at relative electronegativity differences. To throw this back to like relative electronegativity differences, fluorine's going to pull electrons more towards itself in this molecule here because it's more electronegative. And the real charge of fluorine is going to go partial negative when we think about the polarity of the bond, and so the oxygen is going to end up going positive in this molecule. So the oxidation numbers are probably more trying to get us to think about the relative electronegativity differences and the polarity of the bonds, and the F atoms are the ones that end up negative. The O are the atom in this molecule ends up being positively charged. In the case of carbonate, we just have to know, and I think you guys picked this up on this example, is that resonance is going on in this molecule. That's the case of delocalized bonding. So a delocalized bond is where we take this double bond and spread it here and then there throughout the molecule. And so we're going to do that anytime we can sketch these equivalent yet different Lewis structure, or these different yet equivalent Lewis structures, to know that we're just spreading that double bond out at all times across the molecule. This would be another one of those descriptions like nitrate as having a bond order of about 4/3. So all the CO bonds should be of the same length in a molecule like carbonate. So all the CO bonds should be of an order of about 4/3. So the bond order of carbon oxygen bonds, and carbonate ions should be of about 4/3 order. Okay, so let's describe a little bit about bond strengths. We picked up some of this in chapter 5 on how we could use bond strengths. Like a chapter 5 concept that sometimes comes up, like if you want a little bit of a history of our textbook, it used to be only that we would discuss bond strengths in chapter 8. So the old days, we would only cover bond strengths in chapter 8. So this is where you'd see and use the equation to approximate delta H by summing up the bond strengths of the reactants. It's backwards. So you remember this problem from chapter 5 where you take the sum of the bond strengths but of the reactants, and then you subtract the sum of the bond strengths of the products. So this is that weird one where it was the reactants minus products, because what you're saying, what you're trying to accomplish here is to say, how much heat does it take to break all the bonds in the reactants, and how much heat do you get back when you make all the bonds in the products? So you take the reactants minus the products, and this gives you an approximation of the delta H of your reaction. One of the things, though, that's worth discussing here that we've noted a few times already is how there's a link between like single bonds versus double bonds. So look at the carbon-carbon single bond versus the carbon-carbon double bond strength. So notice how the double bond's a lot stronger than the single bond, and then the carbon-carbon triple bond is even stronger. So as you increase the bonding pairs of electrons, you increase the strength of the bond, and that kind of is the corollary to decreasing the bond length. So we probably remember that triple bonds are shorter than double bonds in terms of their length. If you think in terms of the strength now of the bonds, the triple bonds are going to be stronger than the double bonds, which are going to be stronger than the single bonds. So more electron pairs, shrink the bond lengths, strengthen the bonds at the same time. And so that's the other issue that we here by comparing bond strength. So this is more looking at the comparison of the bond length. So we see carbon-carbon single, double, triple. Notice that the bond length is shrinking. The same thing happens if you switch the carbon out with the nitrogen. So the carbon-nitrogen single bond, longer than the CN double, longer than the CN triple. Same thing happens with oxygen. So carbon monoxide triple bond has a relatively short bond length. So the CO bond length in carbon monoxide is really short because we have the triple bond between the carbon and the oxygen. And then if we look at the bond lengths in CO2, we're going to have longer bonds in a case of something like CO2 because just double bonds there. The bond in something like methanol, the CO bond length single bond in methanol. So we're going to expect a longer bond in the case of the single bond. And you pick it up with all different variations as well for NN versus NO versus the OO bonds. So double bonds always shorter than single bonds. Okay, so now let's look at this question here. We're going to have to evaluate a few things for a problem like this. We're going to have to look at some different Lewis structures. We're going to have to consider resonance, and then we're going to have to calculate the sort of bond order we expect, and then we're going to predict the bond length trends as a function of the bond order. So as the bond order goes up, the length should shrink. Okay, so consider coming up with the Lewis structures, thinking about resonance, and coming up with those average bond orders for a question like this one. Okay, so let's take a look at this one. So seems like we got the order right, but whether we have it in one way or the opposite way is the issue. So for NO minus, we get a bond order of 2. For nitrite, hopefully we can all arrive at the same Lewis structure where we have a double bond with one of the O's and a single with the other. Then we pick up that we could have written the Lewis structure the opposite way with the double bond between the other NO and then a single bond with the other double bond being single. So we can imagine that we have those 3 bonding pairs of electrons spreading across the 2 actual bonds. So that gives us a bond order of 3 halves. In the case of nitrate ion, we come up with the 4 pairs of electrons, so 2, 3, 4, that are going to spread across those 3 NO bonds. So here you're counting with the 4 in this molecule, you're counting the bonding pairs, the lines between the N's and the O's, and then the 3, you're counting how many actual bonds there are. So I came up with bond orders of 1.5 and 1.33, and so the 1.33 bond is of a longer bond length because it's of a lower order. So this is getting closer to 1. So single bonds are longer than double bonds. Okay, so our shortest bond is going to be the bond order of 2, then the 3 halves bond, then the 4/3. So we're going to have NO minus be shorter than NO2 minus, which is then going to be shorter than nitrate if we're basing these bond lengths on these bond orders that we get from the Lewis structures. Okay, now bond lengths are complicated trends. Now the key here is that we're just basing this on the bond order trend. Okay, and then remembering that the higher the bond order, the shorter the bond. So let's just go back through a few other types of Lewis structures and kind of note where we get some octet rule exceptions. Some of these rules have to be, sometimes the octet rule has to be broken. Like if we're going to bond 5 fluorines to a single phosphorus, it seems like we're going to have to violate the octet rule in the Lewis structure. So if we take phosphorus, valence count's 5 plus 5 times 7, that's a total of 40 valence electrons. We'll get there by having 5 fluorines. And in chapter 8, we're not really worried about how these atoms are arranging themselves around the central atom. We're just trying to get the count and showing where the valence electrons reside on which atoms. So we end up with 5 F atoms, each with a single bond and 3 lone pairs of electrons. So that's 8 electrons per F. So that's 40 electrons distributed, none left over to go on phosphorus. And so then at this point, all the atoms would have 0 formal charges. So the formal charge of fluorine would be 0. Phosphorus should have 5 electrons surrounding it, and it does have 5. 1, 2, 3, 4, 5. Just cut the electrons in half for formal charge calculation, but then you consider all the electrons that surround a central atom when evaluating the octet rule, if it's obeyed or not. So for phosphorus here, it's now being surrounded by 10 electrons within this Lewis structure instead of 8. So you would say that phosphorus here has an expanded octet. So this case here, so this has an expanded octet within the Lewis structure. Now, these types of compounds tend not to exist without a really electronegative atom on the outside. So you take phosphorus with something really electronegative like fluorine, and occasionally these compounds form with things like chlorine as well. But the fluorines are pulling electrons off the phosphorus. You could sort of think that that's really why this compound exists, is you have something really electronegative that are pulling those electrons back away off of phosphorus. So that on average, it's actually not really being surrounded by as many electrons as the Lewis structure is predicting. So what I like to say is, now the book will say PFI violates the octet rule. But I think that the Lewis structure we sketch violates the octet rule, and then the real atom just uses the electronegativity of the atoms to sort of pull those electrons away from the central atom, so it's really not packing that many electrons around a single atom. Now, a molecule like SF4, I think this is just a reminder. I think we've seen this example already, but we just do 6 plus 4 times 7. The key here is, in order to get the Lewis structure right, sometimes you just have to count the electrons and follow the rule of single bonding the atoms to the central atom first, give them their octets, just to pick up that that's only 32 electrons, that's essentially the only way that you know to throw an electron pair onto the sulfur. So I subtract the 32 used electrons, there's 2 electrons to go, that's how I know to put that electron pair on the sulfur atom. I like to think of them going as a pair, and I like to think of them centered on sulfur. Sometimes by me drawing like a little electron pair helps me remember that those 2 electrons are right on sulfur. So when I'm calculating my bond order, or not my bond order, when I'm calculating my formal charge, that I'm going to picture those 2 electrons as being exclusively on the sulfur atom. So the formal charge of sulfur should be 6 minus 6 for 1, 2, 3, 4, 5, 6 being subtracted off of 6, coming up with the formal charge of 0. Same formal charge for fluorine here of 0. It's just 7 minus 7 for the fluorines. Let's come back to phosphate. We've looked at things like phosphate. I don't know if specifically we've looked at phosphate itself, but phosphorus 5 valence electrons, 4 times 6 plus 3. So that would be a total of 32 electrons. So we have our central phosphorus, 4 oxygens, we give the oxygens their octet with lone pairs. And then that's all 32 electrons, so there's no electrons left over to go on phosphorus, so there's no electron pair on phosphorus. If we're calculating formal charges, we would go plus and then minus all the way around. And I think that this would be the best Lewis structure for phosphate ion. The textbook goes through a weird consideration of, and we've talked about this before as well, of making that extra double bond to reduce the formal charge of phosphorus down to 0 through this type of a bond here. So if we make one double bond, then we still have used 32 electrons, so we haven't created or destroyed electrons. We've now made the formal charge 0 on the central phosphorus and 0 on the double bonded oxygen and minus on the other O's. Now, which Lewis structure is better is almost going to be preempted by what the question says. Like, if I say the best Lewis structure on a quiz, I think there is like a quiz question that's going up for today where it says, in the following molecules in their best Lewis structures, which one has an expanded octet? And there's like one choice that clearly has an expanded octet. And then there's like, I think phosphate is actually one of the choices in the molecule of, so like whenever you're looking at a test, like especially one of my quizzes, like I'm writing my quizzes from where I would usually say this is the best Lewis structure for phosphate. And the book almost says that. If you look at the textbook, the book says, well, some consider this Lewis structure on the right here, draw a box around this structure, and then they almost argue that this is poorer based on theoretical calculations. If you do quantum mechanical modeling, it seems to suggest that you really don't end up with a double bond between one of the O's. And even if you did, that double bond would have to resonate with the other bonding pairs. So a better question for phosphate might be, no matter what resonance structure or Lewis structure you think is right, do you expect all the PO bonds to be equal in length? The answer should be yes. No matter which of those Lewis structures you think is right, you should be able to say that all the PO bond lengths should be equal in bond distance to each other. It's not going to be the case that one's shorter, the other 3 are longer, because we would still at least have, even if you picture this structure here, we would still have the case of this delocalized bonding taking place and resonance kicking in. So I think the one on the left is a little bit better. So I think this is generally the better Lewis structure. But we would usually say that the one with the star symbol is the formal charge rule. So if you minimize formal charges, you would arrive at the box structure. And if you're following the octet rule, then you arrive at the structure on the left. So the structure on the left satisfies the octet rule, and the structure on the right is minimizing formal charges, or supposedly following this formal charge rule. Okay, there's a few other molecules. We've done a few of these where there's exceptions due to not having enough electrons or having an odd count of electrons. So in the case of the OH without a minus charge, we only have 6 plus 1 for 7 electrons. So for that molecule, when we're picturing a single bond between the O and the H, we only have 5 electrons left to go. So we have to be deficient of an electron on one of the atoms. It's going to be the oxygen atom. Now, in some of these molecules, I've mentioned, like with NO when we did this one earlier, that sometimes it's easier to picture the minus charge being there and kicking the electron off. So for like NO minus, we'd have 5 plus 6 plus 1. We did this on one of the examples just a few moments ago, but you'd end up at this Lewis structure here because we're satisfying both atoms' octets, and then we're distributing 12 electrons. And so we end up with a double bond and 4 pairs of electrons. And so then for NO, without the minus charge, if we got to kick one of those electrons off and go to 11 electrons, then we're choosing the O or the N. In this case, we're going to choose the N to remove the electron because that keeps nitrogen with a 0 formal charge, oxygen with a 0 formal charge. And our consideration was if you did it the other way around, if you came up with this structure, you'd have a minus and a plus. So another way of thinking of the formal charge rule is it helps us when we have otherwise equivalent types of structures. We're satisfying the octet rule, in this case, breaking the octet rule equally the same. So we're going to choose the structure that minimizes the magnitudes of formal charge. Now, ClO is actually a tricky case. So let's look at ClO. We have 7 valence for chlorine, 6 for oxygen. If we're picturing Cl and then the O, let's picture ClO minus again. So let's add the extra. Let's picture for ClO minus, we'd have 14 electrons. 14 electrons is just like Cl2 or F2, where we're going to have a single bond and electron pairs. So now which atom do you kick the electron off of to go down to 13 electrons that you have for ClO? So if we got to kick an electron off, let's go through the 2 choices. We can either kick it off the O, or we can kick it off the chlorine. Okay, so we're either kicking it off the O or off the chlorine. Okay, which one do you think's better? So this is actually really tricky. So we get 0 and 0 on the left side. And then we get plus and minus on the right side. The one on the right side, we have 7 electrons around oxygen, should only have 6, so that's how we get minus 1. Chlorine should have 7, only has 6. That's how we get the plus, wondering where these charges come from. Now, again, which of those sets of charges is better? The minimized charges is always better when we're choosing Lewis structures. When we're trying to choose the right Lewis structure, we go with the lowest magnitudes of formal charge, all else being equal. Okay, so this structure here maximizes formal charges. Now, for a second, you think that's actually better. So usually you're thinking, well, oxygen's more electronegative, so why wouldn't it want to be negative? Chlorine's less electronegative, it should want to be positive. We actually get to a better answer starting from this Lewis structure here, and then think about polarity. So like, polarity is best thought of once you arrive at the best Lewis structure, then think about how oxygen is going to pull the electron pairs more closely towards itself, just because it has a higher electronegativity. And in case you forget the electronegativity scale, which I'm sure we don't have the numbers memorized, but F and O are the 2 most electronegative. If you just remember that, you'll remember F and O are the 2 most electronegative, and then it's like nitrogen and chlorine or below them, and like NOF. So if we're thinking of which atoms are the most electronegative, it's these ones here. So if you're thinking of like these atoms here, there's a question on one of the quizzes that gets at like which bonds are polar versus non-polar. If you pair up any of these atoms with anything other than itself, it's going to make for a polar bond. So if you have something that's really electronegative paired up with anything else, the difference is going to have to be pretty big. So these are our most electronegative elements. Okay, so for ClO, we arrive at the structure that has 0 formal charges. Then we can think oxygen ends up being negative, the partial charge on chlorine ends up being positive. So if we start from the Lewis structure, that's the best description of the molecule, then we should be able to think about polarity. If we arrived at this Lewis structure here as being the best one, then we would think that the charge on oxygen would be even more negative than -1, which would likely not be correct. So it's not going to be that polarized to make up a whole electron difference just through bond polarity. Now we've gone through like BF3 before, but BF3 ends up being deficient of an octet, but carbonate ends up not being deficient of an octet. So the difference between BF3 and CO3 2- was just the relative charge on carbon pulled in that extra double bond. So if we remind ourselves of BF3, we have 24 electrons, so we arrive at this structure here, where we don't have enough charge on boron to pull in a double bond. But if we arrived at this structure on carbonate, we did have that charge to pull in the double bond. So we have a positive charge, negative electrons, we make a double bond for carbonate, and then we don't do that for the boron, for the BF3 case. So BF3 is fine deficient of an octet, whereas carbonate ends up satisfying its octet with a double bond. For now, I want to look at these 2 examples here. For NCO-, let's look at this Lewis structure here and try to consider if we can get the correct Lewis structure. So we have 5 for nitrogen, 4 for carbon, 6 for the O, 1 for the charge. So that's going to be a total of 16 electrons. And so the order is going to be as given. You know, so that's the one thing that maybe isn't totally obvious, is that the connection of the atoms is as written. So that's how we can know carbon's in the center. So it'll be N, then C, then O. And then if we try our usual outer electrons get their octets, then we're going to notice that carbon has a 2+ charge. There's no electrons left over to go on the central atom, so there's no lone pairs for the central atom. And so then it becomes a question of, do we do this and then this and arrive at this structure where we've now minimized the formal charge? That seems to be better, right? You know, in terms of having 2 double bonds instead of 2 single bonds and a 2+ formal charge on carbon. But what if we had done this instead and made a triple on one side and then left the single on the other? And then lastly, what if we had made the triple on the other side? And left nitrogen with its electron pairs. So if we're kind of picking up, carbon should have 4 bonds. The question is, does it end up doing a triple bond with O, a triple with N, or a double with each? A double with each, like this is what CO2 did. So CO2 did the double with each bond, and we kind of consider this a little bit with CO2 as well. But now let's calculate formal charges and see if we can sort of look at these structures. One of the ways I like to think of it is they're all satisfying the octet rule equally. So all the atoms are satisfying the octet rule. It's just a matter of which one has a better arrangement of electrons. What's the formal charge of this nitrogen here, the first nitrogen? So it should have 5 electrons surrounding it, and it has 6, so it's -1. Carbon's 0. Carbon's 0 in all of these because it's 4 minus 4. And then oxygen's 0 over here. Okay, before we evaluate which one's better, let's calculate the formal charge of oxygen in the next structure down. You see how it should have 6 and it now has 7 electrons surrounding it. So it now has a formal charge of -, whereas the nitrogen is now down to 0. Nitrogen here is 5 minus 5. So just cut the bonding pairs of electrons in half and then count the electrons and think about the net charge of the atoms. And then the bottom structure has a -2. So it's 7 electrons around the nitrogen, but it should only have 5. Or excuse me, it should have 5 electrons surrounding it. It actually has 7. So that's a -2 formal charge. Oxygen is a plus in its formal charge. So can we all agree on which one is the worst? Which is the worst structure? The bottom one is by far the worst, because that's maximized the formal charges. And then the next one would be decided by, well, which atom do you want to put the more negative formal charge on, oxygen or nitrogen? Oxygen, because it's more or less negative. So the one in the middle is actually the better structure. So having a triple bond with the N and a single with the O is a better Lewis structure than 2 double bonds. If we go back to like CO2, for CO2, this was the best structure with 2 double bonds because that gave both the oxygens a 0 formal charge. If we had pictured a triple bond on one side and a single on the other, that would be a plus and a minus now. And that would maximize our formal charges. So we want to minimize formal charges when we're looking at equivalent Lewis structures that are satisfying the octet rule in the same way. The last structure on this page is acetic acid. And this is one where maybe we're getting at this structure just by 4 bonds to carbon. And then I have to put the 2 O's on the same carbon here. Otherwise, I'm not going to be able to give carbon 4 bonds. So if I try any other way, I won't be able to give carbon 4 bonds. So I give each of the oxygens 2 lone pairs and carbon to oxygen a double bond. So I give carbon 4 total bonds, no lone pairs, and each of the oxygens 2 bonds, 2 lone pairs. So there's a few different ways of thinking of Lewis structures. I think when you get to big organic molecules, you're more counting bonds and lone pairs, sketching it together. If you're not sure, you may just do a final valence electron count. You may just count up the total valence electrons, make sure they're all satisfied. All right, guys, that's one for now. And these last questions, I think what we'll do for these ones is pick up with these at the start of class on Friday and then move into chapter 9 after that. All right, guys, have a great rest of your day and a great Halloween. I'm going to skip.